and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. We're going to get right into it today. We're going to wrap up our acid-base equilibrium unit today with discussions about how we choose these acid-base indicators for our acid-base titrations, all right? And again, I definitely want to stress this vocabulary alert, if you will, and discuss the difference between equivalence point and endpoint, all right? So it's really important, and I want you to write this down: indicator, signal, and endpoint of a titration, not an equivalence point. So indicator, signal, and endpoint, not an equivalence point. And so we really want to make sure that we understand the difference between these two things. An endpoint is actually determined by a color change in your titration. So it's the point at which the solution turns from one color to another. And it is a qualitative thing, all right? It's an observance. It's not a calculated value. Now, your equivalence point, let me spell this out. Your equivalence point is when my moles of acid equals my moles of base equals my moles of salt formed, all right? And so that's my equivalence point. This is a stoichiometric point. So equivalence point is a stoichiometric point. Normally, the way that we're going to determine our equivalence point is we're going to use a pH meter, right, that is actually just sitting in our titrate, and we're actually just going to, as the titrant that is added from the burette, it'll actually read the pH and it'll show us. And if we really think about the titration curve that we're going to get, you know, if we were titrating an acid, it would look something like this. And so the pH meter will take ticks along here, and it'll generate this curve, all right? And so once we get that curve generated from a pH meter, we can actually literally just come in here, because the equivalence point is the midway point in this really vertical region, right? So it's just the halfway point in there. And then I've got a particular volume, like if this was 32 milliliters in this particular volume in this titration, right? That means my half equivalence point would occur at 16 milliliters, because it's exactly half the point to my equivalence point. All right, and so determining equivalence point with a pH meter, really easy if I've got access to a pH meter, and then that'll allow me to actually determine the half equivalence point as well, right? So the real question becomes, why indicators, right? So why do we use indicators if a pH meter is actually going to be more accurate and it's going to be able to give us a graphical readout of what we're looking at, all right? So, well, here's why. Indicators are fast, they're easy, and they're cheap, right? And we can choose an indicator to overlap with our equivalence point so that it gives us some precision in the titration, all right? And so the thing that we need to understand about indicators is that I'm going to go ahead and say this. I'm not going to write it down, but indicators are just weak acids themselves, all right? They have Ka values. And so if I'm looking, I'm going to do HIN, with IN standing for indicator. I'm going to show you that this is a weak acid, and I'm actually going to show the dissociation. So we would end up with plus IN minus. And so generally the way an indicator works is this is going to be color 1, and this over here would be color 2. So when I have a majority of HIN, my undissociated indicator, it actually would be orange, and then if I had a predominance of IN minus, it would be blue in this particular case, right? And I would have a Ka value that would actually describe what this particular equilibrium value looks like. And it's important to understand too, when we get in acidic environments, all right, and so when we get into acidic environments, my acid will react, and that's the acid that's in the solution, will react with IN minus to form HIN. So if I'm in an acidic solution, I'm actually, in this particular case, going to be orange, because I'll have a predominance of HIN, right? Okay, so in the basic environment, all right, so in a basic environment, the base that's in the solution will actually react with the HIN, right, the acid form of the indicator, and form IN minus. And so now I've got a predominance of IN minus, and in this particular case, I would expect my solution to be blue. Now, it's really important, too, that I understand that when my pH is equal to my pKa, when pH equals pKa, this is my half equivalence point, that the concentration of HIN is equal to the concentration of IN minus, right? Conjugates are equal to each other at that half equivalence point. And so we really get into the fact that if I have a pH above pKa, and this is the pKa of my indicator, it is equal to, or I'm going to say that, let's put it this way, that means what I've got is that the HIN concentration will actually be less than the IN minus concentration. All right, and that should actually make sense to you, right? Because of what we just said up here. If I'm pH is above my pKa, it's essentially a basic environment relative to the indicator's pKa. All right, and so I would have a predominance of this IN minus, and therefore I would have a solution that is the color of IN minus. Now, if I look at a situation where I've got a pH, let's go ahead and put pH below pKa, and again, this is the pKa of the indicator. In this particular case, if I'm looking at HIM versus IN minus concentration, well, in this particular case, since I'm below, I'm in an acidic environment relative to the pKa, I would expect this to be greater, right? And the solution will be the color of the HIN, right? In the example that I gave you, that would be orange, right? And so it's very important to understand that my color change occurs with my indicators at the point when pH is equal to pKa. This is when my color change occurs. And so how do we select indicators? We select an indicator with the pKa value as close to the pH at equivalence point as you can. All right, and I went ahead and wrote that down for you guys. So select an indicator with the pKa value as close to the pH at equivalence point as you can, right? Because if this is true, this is where my color change occurs, right? So if the pH of that is, if the pH, and this is the pKa of the indicator, right? Okay, and so what I'll see is I'll see my color change that'll occur, and a lot of times it'll overlap with that sharp increase in pH where the equivalence point actually occurs, and the indicator can be a good indication of when I've reached that equivalence point and I can stop. Because really what I'm interested in, ladies and gentlemen, I'm interested most of the time in this amount of volume added, right? And so if this is my pH here, if let's go ahead and just say this is a strong, then I would want something, a pKa for an indicator, right? I would want my pKa equal to 7 for my indicator, and that means I would get a color change in this particular region of pH. Now, generally speaking, a general rule of thumb, pKa plus or minus 1 is normally the range in which your color change occurs. So notice I would expect my color change to occur between pH 6 and pH 8 if I had a pKa value of 7 for my indicator. All right? Okay, ladies and gentlemen, fast and furious. If you have any questions, I hope you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class.